Yes, you can start.
लाइव है क्या?
Yes, sir.
Good evening, everyone. Welcome to the second live session for the Essentials of Turbulence class. You can take any questions now. We'll wait for a few minutes for questions from learners. If there are any questions, we can take those. If you have any questions, now is a good time to ask.
Yeah, I know, but the legal or how will you feel from that? Exactly. You have a trading plan, it is part of technical trading plan. Not trading plan, what about process to it is liquidation.
Any questions from learners? So one of the aspects of turbulence, as you would have noticed recently, is that if you measure the velocity at any point, right? If you measure the velocity at any point and measure it with respect to time, you will see that it is very irregular, right? It varies significantly and irregularly with both position and time. So we take another point, it'll look very different. It'll look very different. So that would be the instantaneous velocity at a single point or with respect to time. That would be the instantaneous velocity. Now this is going to be displaying fluctuations across above and below its mean, right? And typically, you can say that it tends to be, about 25% above or below its mean. So then, if it does that, then so what do I mean by mean, right? Mean means you are actually taking the average with respect to time. And what we are saying is that instantaneous velocity fluctuates by about 25%. Okay, depending on how turbulent it is. But you will see that there are some examples where it varies up to 40%, 50%, 60%, and so on. So that time history of the velocity, what it will show is sometimes it fluctuates a little bit, then a lot. So clearly there is a wide range of time scales. But if you look at the overall process as a whole, U1 and mean of U1 are in some sense, they are stable. Okay, what do I mean by that? You don't see very huge variations of U1, okay? And neither do you see these U1 varying with time. You don't see them spending long periods of time way above the mean or way below the mean. So in that sense, it is stable, isn't it? On the other hand, if you look at just the mean velocity, that sort of stays steady. And that will have a very smooth profile, okay? And especially, we've seen examples where we saw the mean profile for a jet. And in that case, that mean profile is it might remind you of a laminar profile, but it's not laminar. It's the mean of a turbulent profile. So we've discussed this at length that an important characteristic of turbulence is its ability to transport and mix fluids much more effectively than laminar fluids. So then, if that is the case, right, that is what is different from a laminar flow. Now, if you remember Osborne Reynolds' experiment, dye-jet experiment was exactly that, right? He varied the Reynolds number of the clear flow and showed how the dye was mixing more and more effectively as the Reynolds number was increasing. So this effectiveness of turbulence in transporting and mixing fluid is of a lot of importance, right? And that is what makes it an effective tool in a lot of applications. One can say that, pollutant streams in the atmosphere, you see turbulent. If there was no turbulence, then the pollutant would actually take a while to basically get mixed up in the atmosphere. So turbulence also mixes momentum implied by the high wall shear stresses for the aircraft points of turbulent flows than laminar flows. So that will take us, okay, what are the governing equations here? And then, so we have two mainly: the continuity equation and the momentum equation. The energy equation is not something we need to consider because the temperature, we are typically not considering hot flows, definitely not in this class. And we are considering incompressible flows, so density remains a constant. So there's no feedback between temperature and between energy and continuity, right? So continuity and momentum. What are the unknowns? Density remains a constant, so that's not an unknown. Velocity is an unknown. Pressure is an unknown. And that's it. So 3 components of velocity, 1 component of pressure, 4 unknowns. You need 4 equations, 1 continuity and 3 momentum equations. So that makes it 4 equations. 4 equations, 4 unknowns. Can be solved, isn't it? But it's not as easy, right? The nonlinear term in the momentum equation makes it very complicated to solve. So that non-linearity is what is the biggest challenge in solving turbulence. So you cannot get analytical solutions for sure because it's non-linear. Now you make some assumptions and get rid of the nonlinear term. If you get rid of the nonlinear term, then that is something you can explore, but that can be done only for laminar flows. So that's why there are a lot of analytical solutions for say flow between 2 plates, laminar flow between 2 plates, laminar flow in a circular pipe. All those solutions are obtained by assuming laminar flow, of course, and by neglecting the nonlinear term. So we are assuming that the viscous term is so much that the nonlinear term, the inertia term can be neglected. Are there any questions at all? So we'll wait for a few minutes and then we'll wrap up if there are no questions. Okay, so if there are no more questions, I'm going to close this session. We will have one more of these sessions in a few weeks, in about 3 to 4 weeks. And then if you have any questions, feel free to log in and let me know if you have any questions at that point. Okay, thanks everyone. Have a good evening.